Hello, this is Dr. Mac. Welcome to my video. I'm going to talk about central limit theorem. I'm actually work through the example in your textbook 6.5.1. I will ask that if you have not taken the time to look at the examples and read a little bit in the textbook, I would refer you to page 206. Now, and they also give more explanation on what I'm going to talk about, but I'm going to try to simplify what's going on with the central limits theorem stuff. Okay, so first, let me draw you a little diagram to try to explain what it is you're actually doing with central limit theorem. So central limit theorem, which I normally just abbreviate with CLT, central limit theorem is used whenever you have a sampling distribution. So that means you have an entire population and you're going to repeat taking a sample within this population until everyone has been sampled, like every group of N, whatever your N is, has been sampled in every possible combination. Whenever you have I'm going to do two cases to show you what your sampling distribution will become. So let's just say we have a population that is not so normal. So I'm just going to draw like, that's going to be the distribution of your population to represent something that's not normal. So let's just say over here the population is like a mound shape. It's approximately normal. So just assume that's a bell-shaped distribution for your population. So in both cases, it's going to depend on, I'll start on the left first with my unknown distribution, or you can also say not normal. If they don't specifically say normal distribution for the population, assume that it's not normal. Okay, so on the left, this is my not normal population. I will have to take a sample of at least 30 in order for my sampling distribution to be approximately normal. So I'm going to just write approximately normal sampling distribution, because what we're doing is we're creating a new distribution based off of all the different samples that we take from the population, and we do a whole new distribution. Okay, so on the right side, this is whenever my population starts out as normal. And then you can have any size sample. You can have something as small as 2 and just keep repeating the sample of 2. Gather the mean, because I believe this is a sample mean question, yes, because you can do different statistics, but this particular section is about sample means. So you just take samples of small as 2 or 3, and you're just going to find the mean of those 2 particular data points and make a sampling distribution from that. So whenever you find the sampling distribution from a normal population with any size N that you're sampling, you will still have an approximately normal sampling distribution. So I hope that explains when to use central limit theorem, but we're going to, or in what case. And of course our samples are randomly selected. Okay, so let's get into this example. I've also squeezed in another question just so you can see the difference between when you need to use central limit theorem and when you do not for normal distribution. All right, so we're talking about the birth weight of boy babies in European descent who were delivered at 40 weeks is normally distributed with a mean of 3687.6 grams with a standard deviation of 410.5 grams. So I just want to point this out. I want to point out that it does say normally distributed. Get my highlighter. So it does say right here, normally distributed. So when they're talking about the problem and they mention normally distributed, it doesn't matter what the size of the sample is, because we're starting with what we see right here on the right side. Okay, so we're given a mean of, this is population mean. So the population mean, that is a mu So that's going to be 3,687.6 grams. And they're also giving us that sigma for standard deviation, population standard deviation of 410.5 grams. Okay, so suppose there were 9. So they are sampling 9 boy babies, okay, on a given day, and the mean weight is calculated from those 9 babies. So they're giving us a sample size of 9. So just to recall what we're talking about with central limit theorem, if they wanted us to find the standard error or the standard deviation for the sample mean, we have to keep in mind that we have a small sample, so that means the population has to be normal, which it is. So a size 9 is okay for that small sample because we could still take care of our business with the central limit theorem and have an approximately normal sampling distribution. So moving right along, one thing I did not mention was when using central limit theorem and we want to find the mean of the sample, or I should say the mean of the sample means, is equal to the population mean. So what that means is, for our example, if you have a sample of 9 and we took those 9 boy babies, averaged the weights, and we found the mean weight of those 9, and then we did another sample of 9 and we did another sample of 9 till we had every single combination of 9 babies, boy babies that is, in the hospital, we're assuming that's our population, then that will be what you end up with. It will be the population of every boy baby in the hospital, which would be the population mean, would be equal to every combination of 9 means for the babies. And I hope that makes sense, but just know that is equal to the population mean. So if they're asking you for the mean of the sample mean, it's the same as the population mean. And also to note that your standard error or your population standard deviation, it's a long phrase, I know. We're talking about the sample means standard deviation, okay? So this is just notated with the sigma x bar. As you see above, I did put the mu x bar, and that does indicate we're talking about the mean of the sample means. So right now the standard deviation of the sample means is going to be equal to the population standard deviation divided by the square root of n, and n is given to us as 9. So we have everything that we need. Okay, so moving on. What is the mean of the sample mean? So that's just going to be our mu x bar that we just discussed, and it's equal to the population mean, which was given as 3,687.6 grams. What is the what is the standard deviation of the sample mean? So that's the formula that we had right here with that star. So that's just going to be equal to, that sigma x bar is equal to sigma over square root of n. That's the formula to find your standard deviation of the sample mean, which is also called the standard error. So I'll call it standard error from now on because that's so much nicer to say. Okay, so then you're going to put your numbers in. So you have 410.5 divided by the square root of 9, which is 3. So I'm going to get my handy dandy calculator out. Okay, so then you're going to put those numbers in, 410.5, and you're going to divide by the square root of n. I'm just going to put 3 because square root of 9 is 3. And that's 136.83 repeating, so I'm just going to put 136.83. Okay. What distribution is the sample mean distributed as? So since we're talking about sampling distribution, they just want to know with this question, what is the distribution of the sampling, like the sampling distribution, basically what's the shape? Okay. And, is it a normal distribution or is it not a normal distribution? That's the only 2 ways we would really answer this question. So in our case, since we know the information that we have here, You could just say, okay, my population started as normal. So even though my sample size is small, I'm still going to end up with a normal distribution, or you can say approximately normal sampling distribution. I would want you to give me a little rationale with that. So you can say, okay, I'm not going to write it in a complete sentence. I'm just going to say population normal, small n, or you can say, you know, what the n actually is, or you could just say it's less than 30. Um, and then you'll just say, you know, approximately normal sampling distribution. Sampling distribution. Okay, that's supposed to be distribution, DISTR. Okay, so find the probability that a randomly selected boy baby was less than 3,500.4 grams. So this is a question that I kind of snuck in there that your example did not have. Reason being is because I wanted you to see right here, I'm going to highlight it, where it says randomly selected. So when they're talking about just a randomly selected individual, when they want to find the probability, you're going to find the probability according to just regular normal distribution. You don't have to use this adjusted standard error. Okay, so I'm going to make sure you see all the notation, how I would want you to write it, how I want you to show your work if you were to give me this on a midterm, or if you were giving this to me on homework assignment or anything like that. So first of all, probability notation is a capital P, open parentheses. You're going to put the X, which represents your random variable, and it says less than, so you're going to put a less than sign, and then you have your actual number for X, and that says 3,500.4. What I would want you to do, I'm actually going to use my TI-84, which I showed earlier when I was doing my standard error. I'm going to show you what to type in and then what I actually want you to put as showing your work. Okay, so you're going to go to normal distribution, and keep in mind, since it's a randomly selected individual, we are doing regular normal distribution since it is a normal case because it said our population was normal. So I'm going to go to normal CDF because this is a continuous variable that we're dealing with. Now, when we are talking about less than, that means we're shading to the left. If we want to kind of show, well, I'm not going to draw a curve, but you're going to shade it to the left. So my lower is already set at -1 E99 to represent negative infinity. And here I put in my 3,500.4. My mean is given as 3687.6, and my standard deviation, I'm not going to use the standard error version. I'm just using my regular old standard deviation 410.5. Remember, we're not doing central limit theorem on this question. So paste. So everything that was just pasted into your calculator before you hit enter is what I want you to write as your work. Okay, so I'm going to go ahead and hit enter, but then I'm going to write down everything that I see on my screen. Okay, so what does that say? 0.3242, and I'm going to take it to that fourth decimal place. So 3242 is my answer. But I want to give, let me write it down before I forget what the answer is, but I want you to write it out. So I want you to write normal CDF, open parentheses, negative infinity or -1 E99, comma, all the way up to your 3,500.4 because that's the area that's shaded under the normal curve. And then you're going to put your mean and standard deviation. So your mean is 3687.6 and your standard deviation is 410.5. 0.5, close parentheses. This is showing your work for finding the probability, and of course the answer is 0.3242 as we saw in the calculator. So now let's move on to, so I'm going to put no CLT on this one because this was just, straight up normal distribution. So for the next one, I want to highlight that we are now asking to find the probability that the mean weight of the 9 boys, okay, the 9 baby boys. So we are asked to do something slightly different. This is when we have to consider the mean, okay, the sample mean. So since we want to know the probability of a mean, we're not just using a random individual like we did for X. For the last notation, we're actually going to use X bar. Now notice the X bar over, or the X bar that we have in our notation for probability. You're going to use the same normal CDF, but we are going to adjust the standard error. So you have normal CDF, negative 1E99, and I'll do the calculation in a moment, but I know all of this is going to be the same. So your range is the same. You're going to have, your mean doesn't change because even though this is mu X bar, it still stays the same. Now what's going to be different this time, and we are using CLT, but what's going to be different this time is when you actually take your standard deviation, you're going to divide by the square root of n. So I'm going to go into my calculator and then I'm going to make that adjustment. So second bars for distribution, go to number 2 for normal CDF, and when you come here, come down to your standard deviation, you're going to take that and you can just either use what you found previous for the standard error, or you can just take your standard error and divide it by the square root of n. So you can put the whole square root in there if you want to, like that, or just put 3 since it's a perfect square. They don't always give you a perfect square, so at least you know you can just type it in like this. Then you're going to hit paste. It just pastes it on your main screen here. And then you find that this probability for this happening, the mean weight of 9 boys being this amount, would be 0.0856. 0.0856. So you can see how much lower it would be given that sampling distribution for the mean weight, okay, because it should be a lot smaller. Even though this would be a normal distribution, it would be a lot more narrow because you'd be having a lot of those values clustered right around the mean in the middle. And of course, the standard deviation is smaller, so it'll be less spread. So I hope this is helpful for you. If you have any further questions, please do not be hesitant reaching out to me. Have a good one.